So for those of you that came in late, we can't get access to the projector. So I've started the Zoom call. So if you want to follow along with those slides on your personal device, whether it's your phone or your laptop or tablet, go ahead and do that. We'll start in a couple of minutes, give everyone a chance to get in and catch up. What's up? well, let's get started. It's good to see most of you in person. Still have some people out, which is fine. But just in case any of you do have to quarantine in the future during the session, I'm still going to be doing these, hosting these over Zoom as well. So it'll be a hybrid. So if you do miss anything, or if you do have an absence that you have to have, is the mic on? My goodness. I'm just going to stand over here. Oh, the mic's not on. Somebody's not muted. Make sure you mute your Zoom if you're in the room. Okay, but hopefully we'll have the whole projector thing figured out, so it shouldn't be a problem. And we'll be able to project here. I'll still hold the Zoom during the class session, so anybody that has to quarantine, they'll still be able to access it. Also, it helps to record the session, so we'll be able to, you'll be able to access those for the exam, be able to study and everything, so we'll keep that going. But this week we're talking about earthquakes and tsunamis. So for those of you following along on Zoom, this short video is from San Francisco. This is what San Francisco looked like in 1906. San Francisco at this time was a big boom town, big growing economy, a lot of growth, mainly from initially from the gold rush in 1849, but then all the trade coming in from the Pacific coast. It was like really the gateway to America from East Asia. So it was a big booming town and growing city. But eventually in 1906, we get a huge devastating earthquake, very devastating earthquake. The first one that people in San Francisco truly experienced. And the biggest portion of the damage in this earthquake was from fires. As you can imagine, in 1906, most of the buildings were still made of wood, and all of the lighting was still made from oil lamps. Could somebody mute their, you don't know, do you have headphones? Do you have headphones? No. Okay, here. That might help. No problem. So if you can imagine, San Francisco at this time, they still had oil lamps. All oil was piped into these lanterns that would power their street lights. So during an earthquake, these would fall over, all those oil lines would rupture. And what really damaged San Francisco was the fire. Most of the buildings weren't tall enough to really collapse and do a lot of damage, but the massive fire that happened afterwards was really what was damaging it. So whenever we talk about all these hazards, keep in mind that we're talking about really devastating events, which is sometimes takes the human element out of it. So keep in mind, these are really devastating, but we're going to be looking at these objectively as scientists. So what we're trying to do is understand these disasters and understand these terrible, terrible tragedies in order to prevent new tragedies from occurring. So let's look at San Francisco, two different earthquakes of similar magnitudes. 1906, we have a magnitude 7.9 on the Richter scale. We have over 3,000 deaths. 80% of the city is destroyed, widespread devastation. In 2019 dollars, $11.4 billion of damage that had to be repaired, and a massive, massive increase in the homeless population. Fast forward to 1989, San Francisco is still growing. It's one of the largest cities in America, and it's known a lot about earthquakes and learned a lot about earthquakes. So now we have a similar magnitude earthquake, only 63 deaths, a significant number of injuries, a significant number of property damage, about 13 billion, but that could also be attributed to a larger population in San Francisco. Remember, we're still growing. At that point in time, for San Francisco to have 11.4 billion in property damage, but a much lower population, that's pretty significant. Compared to San Francisco today, 13 billion is probably a drop in the bucket. And this, after 1989, the entire city recovered within 5 years. So we have a faster recovery time. We have less deaths, less injuries, less damage. So San Francisco is a poster child for how we deal with earthquakes. We can similarly look at Mexico City. Mexico City, if you're not familiar with the history of Mexico City, it is built on the sediments of a lake. So all of modern day Mexico City is built on the remnants of this lake, which the Spanish conquered in 1585, I think, somewhere around there. It's where Tenochtitlan was situated, right on that massive lake. But eventually it was all filled in, built up around it and on top of it. So you have all these unconsolidated sediments beneath all of these large buildings. So in 1985, we have a magnitude 8. The epicenter is a little south of Mexico City, and this lasted for about 3 minutes, 3 minutes of shaking, actual shaking. And whenever you have a large scale earthquake, you get aftershocks, which are the little smaller scale earthquakes that happen as a result of that initial earthquake. So around 35% of the city suffered massive damage. You have 10,000 buildings damaged, 3,000 buildings completely destroyed and uninhabitable. Just like what we had with San Francisco, natural gas lines were ruptured. If you can imagine, something that can destroy a building can easily destroy a pipe that's transporting natural gas for heat. So obviously you're going to get a lot of explosions, a lot of fires resulting from that. 10,000 people died in this in 1985. Another 30,000 injured. And because there wasn't enough heavy machinery, rescue efforts and recovery efforts weren't really effective in 85. So we get another one 4 years ago, 2017. We only have 370 people killed. Similar size earthquake, similar distance from Mexico City, but only 6,000 people were injured, significantly less property damage. Only 40 buildings collapsed and were declared uninhabitable. The rest of them were able to be repaired. And this, they got a lot of help from surrounding areas. There was still a bit of a power problem, but they were able to recover it really, really quickly. So Mexico City and San Francisco are both two really, really good examples of looking at past natural disasters and events and planning, policy making, and engineering solutions to prevent these things from happening in the future. You can't prevent the earthquake, but you can prevent infrastructure from hurting your population. So in order to understand earthquakes, we're going to talk about why they occur, where they do, and what it is that causes them to be so devastating. So let's talk first about the location. Earthquakes are typically caused by plate motion. We talked about plate tectonics last week, how the earth is made up of these large interlocking plates that are sliding past each other. They're subducting underneath each other. They're converging and building up mountains. So if you imagine something as large as a continental plate crashing into each other, you're going to cause earthquakes. You're going to cause a lot of friction, a lot of stress and strain and forces that are going to eventually break and snap and transmit that force throughout the earth. So at this slide, we have the North American plate and the Cocos plate, which is what really created Central America as we know it. The Cocos plate is diving down beneath the North American plate. As it's diving down, that subducting plate locks that overarching plate, and eventually that plate starts to spring back up as it gets locked. And that's going to create a lot of these earthquakes that release in energy. The buildup of energy and the release in energy is what really develops an earthquake. This is also one of the fastest moving plates in the world, 76 millimeters per year, which, as you can imagine, 76 millimeters is not a lot, but whenever it comes to a massive rocky body just moving underneath the earth, it's pretty fast. So something to think about whenever we're talking about earthquakes and the damage they do. Earthquakes don't kill people, buildings do. The worst place you can be during an earthquake is inside, just because the physical shaking isn't going to kill you. The physical shaking isn't going to hurt you at all. If you're standing in the fields of Kansas and you get an earthquake, it's not going to matter. You might fall over, but it's not going to matter at all. The thing that has killed people with earthquakes is buildings collapsing and ensuing fires and damage from that. So for the example of the Mexico City earthquake 4 years ago in 2017, the buildings that did collapse, a lot of that was due to poor building codes. Now, the building codes themselves were actually pretty solid. Mexico City has, since 1985, has done really well with enacting policies that are set really good building standards for making buildings earthquake proof and able to withstand shaking for long periods of time. The problem is contractors are able to hire their own inspectors. That means the inspector is incentivized to pass and certify the building, even if it's not actually passable of quality. So that was the problem with those. Remember, we only had 40 buildings collapse during that one, but for those specific buildings, all of them had the same problem. Inspectors that just certified the building without even looking at it. So corruption is a big problem when it comes to building collapses from earthquakes. So if you're looking at your screen, we've seen this map before. This is our tectonic plate boundary map. You can see the Mid-Atlantic Ridge right down the Atlantic Ocean. You can see the Andes built up from the Nazca Plate going into the South American Plate. You can see where the Himalayas are, all of those plate boundaries. I want you to lock that image into your head and then look at the next one. This is a map of volcanoes and earthquakes. So what's something that you can tell me about what you see here? For those of you on Zoom, type your answer into the chat. For those of you in person, what do you think? Do you think volcanoes occur frequently at all plate boundaries? Earthquakes occur at all plate boundaries? Or both volcanoes and earthquakes occur frequently at all plate boundaries? A, B, or C? Who votes A? Just raise your hands in the room. Who votes B? Who votes C? Who didn't understand the question? All right, it's actually B. Earthquakes occur at all plate boundaries. Volcanoes occur frequently. This is a kind of a confusing question. I probably should have taken this out because of the phraseology of it. But earthquakes occur at every single plate boundary. Even if you have plates moving apart, you're still getting that buildup of new material, and that tensional rift is what's breaking them apart. And as they break, that's going to create an earthquake. Smaller scale earthquake, but it's still going to create an earthquake. If you have convergent plate boundaries, as you're diving down and subducting underneath another plate, you're going to get that locking and that springing from the overriding plate. That'll cause an earthquake. And then, of course, with transform boundaries, because those rocks are not perfectly smooth, they're going to catch on each other, and then they're going to build up energy and then shift. And that causes an earthquake as well. So we'll keep that in mind, that earthquakes correlate with plate motion and at plate boundaries. So the main geomorphic and landscape feature that we see from earthquakes and earthquake prone areas is faulting. Faulting is where we have ruptures in overriding rocks and bedrock formations. So they're basically just fractures in the earth where the two different sides of a plate or a rock surface just move past each other. So this is a really good example, and this is something something that you can actually see physically on Earth. This is the curb at, where is it? Rose and Prospect out in California. It's near the University of Cali at Berkeley. This is an example. This road is right along a fault system, right at the boundary of where that red brick meets the concrete. And as you can see, over time, from 1971 to 2005, that concrete sidewalk has shifted ever so slightly to the right. And this has been going on constantly to the point that the city has had to constantly fix it, constantly break down all the concrete, pour new concrete, let it set, and then it keeps going and happening. So that's a problem that the city has not figured out at all. So but it enables us to see and measure actual fault processes on the surface. So whenever we're looking at a fault, we want to talk about its geometry. We want to talk about, we want to be able to describe the moving parts. So what we have is, what we can see on the surface at least, is what's known as the fault scarp. Fault scarp is that cliff that's left whenever one block falls from another one. So it's the surface trace of the fault. It's what we can see on the surface. Obviously in this cross section, we can't see anything below the surface. Maybe if we're mining, maybe if we're clearing a road cut, we might be able to see it, but we can't really see anything on the surface at most fault areas. And most mineable areas don't really involve faults, or you wouldn't want it to involve faults, as you can imagine. If you're a miner, you don't want earthquakes happening right over your head. So this is kind of what fault scarps look like on the surface. It's kind of hard to tell, but you can see right off to the left on the side of this road, there's a clear indication of this hanging wall falling off of it, falling off of the top wall or the foot wall. So something that makes it a little more difficult is that we don't know which one is the one that's really moving. Did the land get pushed up on the right, or did the land to the left fall down and subside? So that's what we're going to start trying to get into. So this is where we have to describe the plane of the fault. So the fault plane is that exact line between the two different blocks that are moving, where the fault is. And that fault plane has an angle, it has a direction, and if we know the direction and angle, we can describe the other two components, which is the hanging wall and the foot wall. So if we look at this image of this miner in this fault, the foot wall is what the miner could walk on. Think of walking feet. This is the portion that's lower. It has that steep angle where the one is overriding the other. So the foot wall is what that miner could walk on. The hanging wall is above the fault plane. So it's what the miner could hang his lantern on. So hanging wall, foot wall. Keep that in mind as we go forward. That's how we'll describe a lot of these fault systems. So we have different types of faulting. So a normal fault is where we have that extension in two different directions. So one is going to, these fault planes are going to, these blocks are going to pull apart, and one is going to slide under the other. The hanging wall is going to slide down. The foot wall is going to stay stable. If we have a reverse fault, or also called a thrust fault, they're pushing together. So if you imagine the hanging wall, it's going to be the most mobile, the most unstable. So it's going to override the foot wall, seen here on the right. And then strike slip faults, where we have motion along that fault plane. Rather than being against the fault plane, we're going along it. That's kind of like think of a transform plate boundary where they're sliding past each other. So we'll go in detail on each of these. So this is a normal dip slip fault. Whenever we're talking about dip is just the direction of the fault plane. So if you think of a piece of paper and I dip it in a certain direction, this is the dip direction. So this is the dip of that fault. So we have an extension of this fault system, which is why the hanging wall is dropped down. Because they're being pulled apart, it enables subsidence. If you stretch things out, think of Laffy Taffy or saltwater taffy. If we pull it apart, what's going to happen to the center of it? It's going to fall down due to gravity. So that extensional stress that we're adding to it is going to enable that subsidence. Now, same thing if we reverse that. So if we take that Laffy Taffy, we take two sides of it and we start pushing it, it's going to start building up in the center, right? It's going to kind of get smushed in. Same thing happens in a reverse fault or a thrust fault where the hanging wall gets pushed up onto the other one. So that's where we get these like angular fault scarps that you can see on the surface. All right, so take a look at this picture here and see if you can identify, there are a couple of different fault planes here. So go ahead and look at it, see if you could figure out where the fault plane actually is, or the main ones. So take a second to look at it. That's probably a main one right there. So which one is the hanging wall and which one is the foot wall? As you're looking at it, which one is the left one the hanging wall or a foot wall? Foot wall? All right. Who else thinks it's the foot wall? The one on the left. I see some tentative hands. Who thinks it's the hanging wall? All right, let's see. He's right. It's the foot wall. Well done. So the reason we can tell that this is the foot wall is because this is the one where if you're looking at that fault plane and think of you're walking along that, think of if that was a cliff side. If you're walking along it, this side of it, you could actually walk on. This side of it, you would have to hang on like a rock climber. So we have the foot wall and the hanging wall right there. Well done. So we can see that there's a clear offset in that, and this is what helps us to identify fault planes. Sometimes there are fractures in the rock that aren't associated with faulting. If we can see a clear offset in layers of similar bedrock types, like both of those kind of look like siltstone, those like more brownish layers, those look like siltstone. We can see there's a clear displacement and we can identify which layers line up and how far that displacement is. So based on this, because those layers on the hanging wall have descended, we can tell that this is a normal fault. If they've descended on the hanging wall, that means there's a pull in this direction and there's subsidence. So that's a normal fault. Okay, so this one's a little more tricky. So there's our fault plane here. So we have the cliff to the left and the stable stuff to the right. So is the left side the foot wall or the hanging wall? Anyone want to take a stab at it? 50-50. You think it's the foot wall, the left side? Okay, who else thinks it's the foot wall? Who else thinks it's the hanging wall? Okay, in this case, it is the hanging wall. So if you imagine, since this side is dipping down, you'd be able to walk on this side. So this is the foot wall here, the hanging wall over here. So I'm trying to think of a better way to draw it out that might be easier. Let's see. So if we take away the rest of that block, so this is our whole fault system. If we take away the hanging wall, we're left with a slope, right? So if you think of a slope like this, you could walk on this. If we put this back and we took away our other point, we couldn't walk on this, right? Because this surface is upwards. So we would have to hang on it like a rock climber. So that kind of helps to visualize which is the foot wall, which is the hanging wall. footwall you can walk on, hanging wall you can hang on. And whenever it comes to normal or reverse, we're just talking about which direction this has moved. Did this hanging wall move down? Did it move up? Or did it not move at all? So that's what we're looking at. Does that make a little more sense? Okay. Okay, so let's identify the layers. Most likely those brownish layers of interbedded siltstone that we see there. So based on where the hanging wall is, which direction did it move? Did it move up or down? Raise your hand if you think it's up. Raise your hand if you think it's down. It moved up. So because it moved up, that means the hanging wall is being thrust up over the foot wall. So that means it's a reverse fault. So now in this example, we have a normal, this is a question. I don't like this picture. It's hard to tell what it is, actually. Okay, so for a strike slip fault, this is what we have going on in San Francisco and Southern California. This is a very common type of fault where the two walls are basically vertical in respect to each other. You can't see a visible fault scarp on the surface, so you can't really tell if one is overriding the other. The only thing that you can see on the surface is displacement of features. So if you look at the model here, you can see that those layers of green and those layers of brown are offset. That's the only thing that you can see on the surface, the displacement of features. But whether it's rock formations, maybe it could be a road or a sidewalk, that's the only thing you can see. They're just sliding past each other and bringing everything else on top with it. So you can see a lot of these in the farms in Central California, mainly because all the farms are plowed in very straight maintained lines. And as soon as the fault displaces that, it's easy to tell where the fault is. So we can easily identify that the fault line is right there, where that displacement is. Now, this is where we're going to get back into, if we remember from our last class, which direction it's going. Where we're standing on one side, we're looking at the other one, and what direction that displacement is. So based on this picture, do you think that the other block has moved to the left or to the right? Think of the perspective of the guy taking the photograph. Did the other side move to the left or the right? Who thinks left? Who thinks right? All right, very good. It's to the left. So based on no matter which side you're standing on, if we're standing on this side, we can see the other side has shifted to the left. If we're standing on the other side, we're going to get the same perspective. So whichever side that you're standing on, always think about what the other block has done. Think of the block that you're standing on, it's not moving at all. Which direction did the other one go? That's why we call it right lateral or left lateral. No matter which side you're going to be on, it's going to be the same. All right, and this one, this is the Taklamakan Desert in China. So if we're standing on, pick a side, it doesn't really matter. If you're standing on one side, what direction did the other one move? Did it move to the left or to the right? Who thinks left? Who thinks right? Who is still unsure? Okay, it's to the left. So think of you're standing on that like bright pink formation there, and you're looking across the fault. What did the other bright pink formation do? Where is it in regards to where you're standing? Let's try another example on the board. Let's do it this way. So So let's say we have a river. So this is a river. This is the fault plane. At one point, this river was right in line, but now there's been an earthquake that caused that displacement. So if we're standing right there and we're looking at the other block, which direction did it move? To the left or to the right? Right. Right. Very good. Because compared to where this is to the right. Good distance. If we're standing over here and we're looking at these two, which direction did it move? Right. Right. It's the same from whichever one you're standing on. So no matter which one you pick, it's going to be the same. It all matters. It all depends on where the displacement is going, what direction the displacement is going. Does that help make sense? All right. Beautiful. All right. So whenever it comes to earthquakes, a lot of it has to do with elasticity and the what's the word I'm looking for? Characteristics of the material itself. Whichever type of rock it is, whichever type of sediment or soil it is, they all react differently to different stresses. So this is where we're getting into stress and strain. So stress is the external forces on an object. If I am pushing on this table, I'm exerting a stress on it. Strain is the deformation caused by that stress. So if I push on this table to the point that it breaks, which I can't because I don't have the muscle mass to do, it's permanently deformed. That's the strain of it. Since I'm not breaking it in half, it's not experiencing strain. It's only experiencing stress. So stress, as you're applying stress, strain builds up. So if stress is increasing, strain is also increasing until you get to the yield point, which is known as the breaking point. So every material on Earth has this point. It's different for certain materials. For example, a rock probably has a greater breaking point than a piece of wood, as you can imagine, but every material on Earth has one. So if you think about yourself as a college student, you have stresses in your life. You have tests, papers. You have your relationships with your family, your friends, financial situations. Those are external forces. Those are stresses. Strain is that increasing discomfort that you feel inside of you as those stresses keep piling up until you reach your breaking point and you snap at your roommate or whatever. So stress is the things that are causing that internal discomfort. Strain is the internal discomfort that you're feeling due to those stresses, if that helps make sense. So we're going to apply this to rock formations because rock formations are constantly experiencing stresses, and each rock formation has a different breaking point of those stresses. So they're all building up strain because of all these external forces. That plate motion is pushing them together. Eventually, they're going to reach a point where they're going to break or snap, and that break is what causes a fault or a fracture that we see on the Earth. So if we're thinking of this in terms of energy, that breaking point is where the potential energy is greater than the static energy. Static energy is just the friction of the materials together. Potential energy is that strain building up in the material. So if we're looking at this rebound theory in practice, here we have a regular road at a certain time. The road is built, it's nice and straight, there's no problems in it at all. We're going to start building up stresses in it. We're going to start increasing the strain as more stress is applied. So you can see that road starting to bend. It hasn't broken yet, but it's starting to bend. So this is where we have our potential energy. We're increasing our stored energy. We're increasing that potential energy until we get to the point that we get kinetic energy, where the potential energy is greater than the static energy. We're going to get that slide, that breaking. And now the road is broken in two. Then we get the system reset, basically, because we've finally released all of that pressure, all of that strain. We're basically back to square one, where we don't have any stresses built up yet, but it's going to start building up more stresses again. So at this point where we have no forces acting upon it, but we're going to start, because as with everything on Earth, the rock cycle is cyclical. Like this example. So all of these models that we have make these pretty pictures of fault planes being really smooth surfaces, these really straight surfaces. If that was true, we wouldn't have as many earthquakes as we do on Earth. It's really the friction, the irregularity of those fault surfaces that gives us the surface that we can catch things and then build up that energy. So because of the geometry and the surface friction that we have between these two blocks, that's what's going to give us all of our faulting and all of our earthquakes. Yeah, we can skip over this. Talked about this. Okay, so now we're getting into the actual earthquake portion. All that stress and strain that we've built up, that we finally reach the breaking point where something snaps, that's where our earthquake is. That energy that gets released from all that buildup of energy, that's our earthquake. So earthquakes are released at depth at something known as the hypocenter. That's the actual source of the earthquake. That's the very exact point inside of the earth where the earthquake happened. If you draw a straight line from that point all the way to the surface, that's the epicenter. That's the point we care about the most, because when we want to map out earthquakes, that's the easiest one to find. All right, tell you what, it's 10:45. Let's meet back here in 10 minutes. Go ahead and take a break. Just stretch your legs, get some water. If you have to use the bathroom, go ahead. And we'll get back into talking about seismic waves, that energy that gets released from earthquakes. So see you back in at 10:52.
Quick question about last slide that you had up.
Yeah, sure.
So you were talking about when the energy potential is stored, that's when the road starts to bend.
Yes.
And then is it when the kinetic energy